Hi. Today I wanted to play a little bit around the known examples of harmonic functions, the Poisson kernels and so on, to see how it all looks, what it looks like. So let us start from the problem. The first example, which was a problem, it is the following. So examples of harmonic functions. It is the following. Consider 2 points in the plane, A and B, and the variable point x. And consider this angle which is formed by the rays xa and xb. It is, say, phi of x. And it was proved that phi of x is a harmonic function. So how can we use this fact to have some insight into the nature of Poisson kernel? Now let us consider 2 points. Say it is, say, x1, it is x2, and 2 points, say, minus epsilon over 2 and epsilon over 2. So these are the endpoints of a segment of length epsilon. And let it be A, this is B, and for any x in the upper half plane, we have this angle, phi, and so this is a harmonic function in the upper half plane. So delta phi of x is 0 in R2 plus in this domain. What is on the boundary? Phi of x equals, here this angle is 0. X 2 equals 0, x1 is less than minus epsilon over 2. Here it is also 0 if our x is here. 0, x2 equals 0, x1 more than epsilon over 2. And in between this angle, if you consider the point here, so xa is looking to the left, xb to the right, and the angle is equals pi. Pi, x2 equals 0, x1 between minus epsilon over 2 and epsilon over 2. Yes, so this function here is looks like this: minus epsilon over 2, epsilon over 2. Here it is 0, here it is 0, and here it is equal to pi. So this is a function. this function. Now if you consider not only this function but also its shifts, then we can consider a function, any function g of x1, yes, and we can approximate this function by this piecewise constant function, yes, which is constant on the segment of length epsilon. So it is, say, 0, it is minus epsilon, it is minus 2 epsilon, it is epsilon, 2 epsilon, and so on. And then we consider the function g of f, let us n epsilon equals, so consider the function sum g of n epsilon times, how to denote this function? Let us denote this function gamma of x1. Yes, gamma of x minus n epsilon. Yes, so each term here, so n from, say, minus infinity to plus infinity. This term is each term is this function, which is shifted by n epsilon and multiplied by gamma of x minus n and g of n epsilon. It is the value of function g of x in the middle. And correspondingly, we can consider the function sum g of n epsilon phi of x1 minus n epsilon x2, and from minus infinity to plus infinity. Yeah. So this is a harmonic function. Each term is a harmonic function. So the sum is also a harmonic function, and it satisfies, let us denote by this, by u epsilon of x, 1, x2. It satisfies delta u epsilon is 0, u epsilon on x2 equals 0 on the boundary equals some this function. Let me denote this function. Let us denote this function g epsilon of x1, g epsilon of x1. Yeah. So this way, using this function phi as the building block, we have constructed solution of Dirichlet problem, this Dirichlet problem, where the boundary function is such a piecewise constant function. Yes? And now, if the function is continuous, no, say, smooth, uniformly continuous on the whole x-axis, say, going to 0, yes, so that everything makes sense, we can say that u of x equals limit when epsilon goes to 0, u epsilon of x. It is solution of the Dirichlet problem, delta u equal 0 in R2 plus, u for x2 equals 0 equals g of x1. Yeah? So we started from this approximation, no, it's a rather crude approximation of a continuous function by piecewise constant function. And then we pass it to the limit and have this solution. And now we can look at this picture a different way. We can look a different way. So this function gamma of x1, let me write gamma epsilon. It depends on epsilon. Consider the function gamma epsilon of x1 times 1 over pi epsilon. This function has the following form. It is minus epsilon epsilon, and here this function is, no, I cannot draw it high enough, it is 1 over epsilon. Yes, because it is pi, I divided by pi epsilon, so it remains 1 over epsilon, minus epsilon over 2, epsilon over 2. So the total integral of this function is 1. No, it is again not the same as the modifier. Modifier looked like this, it was a smooth function. No, it is also some crude approximation to modifier. And we can see that limit it is how to denote it, psi epsilon of x1. Psi epsilon of x1 when epsilon goes to 0 is delta of x, in the sense that this function is 0 everywhere but at the point 0, and the integral remains 1 for all epsilon. Yeah? And so next problem is for this each psi epsilon, we consider the function v of x such that its delta v of x equals 0 in R2 plus, and v on for x2 equals 0 equal delta of x1. Yeah. And correspondingly the function v epsilon of x satisfies the same, but for v epsilon, so Laplacian v epsilon equal 0, and v epsilon x2 equals 0 equals this function psi epsilon of x1. So this function psi epsilon of x1, the point x1. So how can you find this function? No, let us do it. minus epsilon over 2, epsilon over 2. And here the point x1, x2. Yes. So first, let's find this angle phi. And let us not find, let us find it approximately. And asymptotically when epsilon is small. So how to do it? First of all, let us drop a perpendicular here, and let us draw here the segment from x1, x2 to 0 equals x. Let us consider this angle, say theta. And then this perpendicular is, let us denote it by d. And so d equals, no, approximately equals. How to do it? The angle phi is small. Angle phi is small. And so we can say that this curve, this line is approximately parallel to this line. They form an angle phi over 2. So with a small error, which you can estimate yourself, d is approximately epsilon times cosine theta. Yeah? Epsilon cosine theta. And d epsilon cosine theta, and hence the angle is the following. If you have this picture, it is perpendicular, say, to the bisectrice. This angle phi is approximately equal to a ratio of this d to this segment, which is model of x. So this means that phi is approximately equal to d divided by length of x, the distance from origin to the point x. Yes? Which is equal, again approximately, to epsilon cosine theta divided by model x. Yeah? And let me write it, epsilon cosine theta times model x divided by model x square, which is equal to epsilon cosine theta, cosine this theta, times model x is simply x2. x2 divided by model x square. Yeah? So we have this epsilon. So our function phi is this. Now we have to divide it by epsilon to, one moment, yes. So this is our function phi, phi epsilon. When epsilon goes to 0, the error goes to 0 much faster. So now we write psi epsilon of x. Psi epsilon. Psi epsilon was something on the boundary. So on the boundary, this function behaves like this. Yes? So it is exact value on the boundary. So this means that to normalize this function, we have to divide it by 1 over pi epsilon. So u epsilon of x equals 1 over pi epsilon phi epsilon of x equals 1 over pi x2 divided by module x square. Now, again, it is approximately because we used this approximation far from this segment, from this segment where this function, this angle becomes much larger than here. But as epsilon goes to 0, this area shrinks, and so when epsilon tends to 0, we have this limit. And if you consider this function, then, I mean this function, phi epsilon. So again, what was the logical scheme? We defined exact function phi, phi epsilon. It is a function like here. Then we got an approximation of this function phi epsilon, which works outside of this segment, farther from this segment. But when, and this function phi epsilon satisfies condition this condition that its boundary value at x2 is 0 is this function psi epsilon. And when we take the limit epsilon goes to 0, the boundary value of this function tends to a delta function, and the function itself tends to this one concrete function, which is now familiar h of x, Poisson kernel. And now if you are solving the Dirichlet problem, one moment, let me erase something. Dirichlet problem, delta u equals 0 in R2 plus, u x2 is 0 equals g of x1. Yes, the Dirichlet problem for Laplacian equation in the upper half plane. Then solution is u of x1 x2 equals integral from minus infinity to plus infinity, g of y1, h of x1 minus y1 x2 dy1. Here h is this, just this concrete function, which formula we had already last time when we consider it, but that time we derived this formula from the general theory, the general method of reflection and differentiating the Green's function on the boundary. And here you see how to visualize this formula simply. Very good. What can else be done with this formula? What else can be done? Consider this function h of x1, x2 equals 1 over pi x2 x1 square plus x2 square. We can, first of all, we can generalize it to higher dimensions. Suppose we have the following problem. In R3, x1, x2, x3, consider the upper half plane R3 plus x3 more or equal than 0. So it is the upper half space. Yes? And consider some domain in the on the boundary in the x1, x2 plane when x3 equals 0, say domain D. We have domain D. And now it is consider x equals x1, x2, x3. And consider, I would say, the solid angle, yes, solid angle formed by the rays from the point x to the points of this domain D. Yes, it's like this. So, solid angle, know how to define it. Let us take a unit sphere around this point x. So, these rays will intersect this sphere and form some domain on this sphere. Yes? Say domain D prime on this sphere. And the solid angle is the area of this domain, a spherical area on this domain. So this solid angle, say phi capital X, solid angle by which the domain D is seen from the point X. Yes? X in R3 plus. So take any point X and consider this solid angle. And this is the function phi of x. And my statement first, that Laplacian phi is 0 in R3 plus. So it is again a harmonic function. And second statement, that phi for x3 equals 0 is the following. 0 if x1, x2 is outside of D, yes, and it equals pi if x1, x2 inside of D. Now, first of all, the second statement is easy to see. So if x approaches the boundary x3 equals 0, yes, then you can imagine that this cone becomes more and more flattened, and its solid angle tends to 0. Yes, if you go this way. If you go this way, so that your point is x tending to this boundary and tending to some inner point of this domain D, then this angle will open more and more and tend to half space. And the half space, I'm sorry, it is 2 pi. I'm sorry, it is 2 pi, because the solid angle for the half space, yes, is the area of half sphere, which is equals to 2 pi, area half of unit sphere. Yeah, so the second part is clear. What about the first part? The idea is the following. So this is the boundary, this is our domain D, and let us divide this domain D into very small cells like this. Cell a piece of size epsilon, so say it completely gets in say a square of size epsilon, and consider just one piece like this. So we have one small piece, yes, this is our domain, and then we have a point x equals x1, x2, x3, its coordinates, and consider the solid angle under which we can see this small piece. Then again we draw, say, a segment to the center. No, what is center? No, any internal point of this small cell. So it is point, say, x1, x2. x1, x2 is here. Let us be point y1, y2, 0. This is the point. Then equals y. Then the solid angle can be approximately written that this solid angle, say phi approximately equal model x minus y times cosine of this angle alpha, cosine alpha. It is nothing but cosine alpha. It is this segment. It is x1, it is x1, x2, 0. Its projection. So it is right angle. It is simply x3. Yes. I'm sorry, times the area here. Say this area is epsilon. No, we have to go the distance x3. X minus y, approximately. We have to take the perpendicular section of this cone and take the area of this section. This area is d. D divided by x minus y square. This time is square because we are in the space. And d equals epsilon cosine alpha. D is epsilon cosine alpha divided by x minus y square. Yes, and cosine epsilon and cosine alpha equals x3 divided by x minus y. X3 divided by model x minus y epsilon times epsilon x minus y square, so epsilon minus y cube. Yes, so it is something familiar, and so this function phi is this function which is harmonic. It is harmonic because we can simply substitute it and find in the equation, find that its Laplacian is 0. Yes, so it is a harmonic function, and then we have phi equal 0, and phi 1x3 equals 0 is again 0 when y if x1, x2 is not in this domain D, and it is 2 pi when x1, x2 in domain D. So it is a sort of solution for a small piece of D. Let us now denote this piece D number n. Yes, we have piece, just enumerate these pieces. And so we write phi n equals epsilon n x3 divided by module x minus yn square. And this is sort of elementary solution for just a small piece number n. And phi of x equals sum phi n of x. N say from 1 to n capital. Yes? And each term here is a harmonic function. On one hand, again, we have to separate logically. This is true farther from the boundary, where we can use this approximation. So here the function is harmonic, no, approximately harmonic, but when epsilon goes to 0, it becomes closer and closer to harmonic, and the error goes to 0 faster than this term. And this boundary condition is exact condition for this geometrical picture. It is really the boundary value of this solid angle. No, okay, and now we can write. So, what is the boundary value of the function phi of x is exactly what is written here. If 0 in the total domain D and outside of domain D, and 2 pi inside domain D. Yes, so this is done. Now let us move still other direction and record geometrically the Poisson kernel inside a disk, a two-dimensional ball. So,
yes, this.
uh-huh. No. To be for simplicity, consider the disk of radius 1. It is our ball of radius 1, gamma is the boundary. So it is x1, it is x2. And consider here first the function let us consider 2 points A and B on the boundary, on the circle, and for any point x, consider this angle phi of x. And we know from the problem in your assignment that phi of x is harmonic. In B. Delta phi is 0. Now what about the boundary value? If you take, let us divide our boundary in two parts. Gamma 1 is this arc from A to B, and gamma 2 is the complementary arc. Yes? And now, we know from the elementary geometry that if a point is, so here we consider the central angle from the origin to the points A and B, it is B minus A. Now I denote by A and B the central angle. Yes? If you consider phi on gamma 2, it is this angle. We know from elementary geometry that this angle is just half of the central angle, equals B minus A over 2. And phi on gamma 1, if you put it here, this angle is more than pi. This is this angle, and this angle is by the same elementary geometry pi plus B minus A over 2. Look at the textbook for high school, where this theorem is proved. So, so we have again a harmonic function inside a disk such that its boundary value is this piecewise constant function. Here this function in gamma 1 is this pi plus by minus A over 2, and on the complement is just B minus A over 2. Now, using some simple manipulations, we can restore the Poisson kernel. How to do it? First of all, let us subtract this B minus A over 2. So U of x equals phi of x minus B minus A over 2. And so U on gamma 1 equals pi. U on gamma 2 equals 0. Yeah? It is the first step. The next step, let us normalize it. Let us do the following. Suppose that the segment gamma 1 is small. Its length is epsilon. Now let me draw it this way. It is all the same where to put this segment gamma 1, so it goes from minus epsilon over 2 to plus epsilon over 2. And this is gamma 1. And all the rest is gamma 2. And consider this function u of x. It is this phi of x minus epsilon over 2. So u of x equals phi of x minus epsilon over 2. And now let us find how to. First of all, if you consider this exactly this function, then this function is harmonic. It is 0 on gamma 2. It is say this gamma 2. It is equals to pi on equals 1. So u on gamma 1 equal, it is pi yes, it is pi on gamma 1, 0 on gamma 2. Now let us evaluate phi of x. Again, we find approximate value of phi of x, but it becomes precise, more and more precise when epsilon goes to 0. So draw it more realistically this way. Say this x is here, it is minus epsilon over 2, it is epsilon over 2, it is gamma 1. Let us say this point, no, its coordinate is 1, 0. It is 1, it is y. Yes? No, I don't write this, draw. X equals x1, x2. Again, it is alpha. This angle, we have again to evaluate this. It is this, no, let us call it d. D approximately epsilon cosine alpha, and epsilon cosine alpha, and phi of x approximately d divided by module x minus y, yes, and epsilon cosine alpha equals epsilon cosine alpha divided by module x minus y, which is equal epsilon module x minus y cosine alpha divided by module x minus y square, yes, and x minus y, this length time cosine alpha, is simply this, cut it from the origin to the point y, which is 1, 0, and so it is equal to 1 minus epsilon 1 minus x1, yes, it is 1, it is x1, divided by model x 1 minus 1 square plus x2 square. Now u of x. We have to subtract here epsilon over 2 equals u of x equals phi of x minus epsilon over 2 equals u phi x minus epsilon over 2 equals epsilon 1 minus x1 y minus x1 square plus x2 square minus 1/2, yeah? Epsilon 1 minus x1 minus 1/2 1 minus x1 square minus 1/2 x2 square divided by y minus x1 square plus x2 square equals epsilon 1 minus x1 minus 1/2 plus 1/2 times 2 x1 minus 1/2 x1 square minus 1/2 x2 square 1 minus x1 square plus x2 square so x1 goes 1/2 equals epsilon over 2 times 1, this and this go, minus 1 x1 square minus x2 square 1 minus x1 square plus x2 square epsilon over 2 1 minus module x square and x 1 0 it is y, so I write module x minus y square. Whew. Okay, so we found this. So this function is harmonic. No, why it is harmonic? It is harmonic because we found that if you forget about this factor, then this function is a limit, it can be approximated by harmonic functions. So first of all, this function alpha phi is exactly harmonic, and now this is a limit of harmonic functions, if so the limit of this function is a harmonic function on one hand. On the other hand, it is the function itself is harmonic. So this function is harmonic, and on the boundary it has the following: u on gamma 1 equals pi, u on gamma 2 equals 0. So it is almost all we need to have. We want to have it a delta function. Yes, so if you normalize it, so multiply it by 2 over epsilon, so the function 2 over epsilon u of x u equals, say, v of x. Yeah. So this function has the limit 2 pi divide 2 pi limit pi, so pi, yes, v 2 divided yes, v of x, and v of x, so I multiplied by this constant, v on gamma 1 equals exactly 1 over epsilon, and v on gamma 2 is again 0. This and the length of gamma 1 is just epsilon. So we have on the boundary condition is a function which is epsilon here, and the is 1 over epsilon here, and the length of this say arc is just epsilon, and approximately this function is this one moment. So we have Laplacian of v of x is identically 0 in our disk B. B is a ball, no two-dimensional ball. Now v on gamma 1 v epsilon equals 1 over epsilon. V epsilon on gamma 2 is 0. And so, and v is approximately equal. So if you divide this by 2 divided by pi epsilon, 1 over pi x minus y 1 minus model x square divide model x minus y square in B. This, and on the boundary, so when epsilon goes to 0, then v epsilon goes to v equals this function 1 over pi 1 minus module x square module x minus y square, and v on gamma equals delta of x minus y. Now, in our computations, I put y in the particular position here, y equals 1, 0, but in the answer, this concrete coordinates of y somehow drop out. We don't need them. It is purely geometrical, just the distances. So we can substitute here any other boundary point y. That's it. So we recovered the Poisson kernel, and can you write that v equals h of xy. And again, if you solve the problem Laplacian u equals 0 in B, u on gamma equals g of y, then solution is u x equals integral over gamma g of y h of x y d l y. L, because it is a circle, so instead of area I write just the length. So this way, what was the purpose of this all this presentation was to show how we can understand the Poisson kernel, which is a really important thing, in terms of this elementary example, elementary geometrical example. No, I hope I somehow explained it. So for now, let us finish this small half lecture, half tutorial. Have a good time. Bye.